Okay, so I just did a trial. Everything seems to be going well. The screen sharing is working fine, despite some slightly psychedelic effects. So let's get going. Okay, trig equations. Key thing is you need to know the tools. You need to have your toolbox ready, and then your brain switched on to think, given the context of the question. But if you don't have the tools with you in the toolbox, you're going to be stuck at some point or another. So let's share the screen. I'll share my whole screen and let's get started. So I'll post this also. Yeah, that's the sort of psychedelic effect I was talking about. This is a one-page summary of what you need to know. This is your toolkit. Read it. Read that. Got it? You know everything you need to know. What does it mean? Let's go into some depth. Okay, so the first one is if I know one trig ratio, I can work out the others. And I can do that using Pythagoras, because I remember that this all started, the circles and the waves that resulted from those circular movements, with SOHCAHTOA to define a circle. X squared plus y squared equals 1, or r squared, the radius squared. And if I called this angle theta, I could say that sine theta was equal to the opposite over the adjacent. Sorry, hypotenuse, opposite over hypotenuse. Well, what's opposite theta? So if we're working with theta, it's this side here that's opposite theta, the 1. And the hypotenuse is always the side that's opposite the right angle. Okay, so that's h. We don't know h, but we do know the opposite's 1 and the hypotenuse is h. Could we work out h? Yes, we can, and that's where Pythagoras comes into play, because we know that h squared must equal 3 squared plus 1 squared. And so if I just want h, all I have to do is square root both sides, and 3 squared is 9, and 1 squared is 1, so actually h is the same as the square root of 10. And with that, I can now say, great, well, sine theta I know is 1 over root 10. So if a question had told me, hey, I'm going to be a bit tricky, and let's say they didn't show you this triangle, and they just told you that tan theta was equal to 1/3. Remember, that's tan theta is opposite over adjacent. So the 1 must be the opposite, and the 3 must be the adjacent. You could have quickly sketched the right angled triangle, chosen theta to be wherever you like. It doesn't have to be up there. All that matters is the opposite is over opposite the angle you're talking about, and the adjacent is next to it, and then you've set up your triangle, and you can use Pythagoras to find h, and hence find sine theta and cos theta. And that's a typical question. They'll tell you one of the ratios, and you need to set up this triangle and use Pythagoras to find the others, the other ratios, that is. Okay, and then I'm going to skip straight from slightly unusual. I'm undoing all of this just so we can get that a bit less messy. So I could also say, well, okay, now that I've worked out that this h is root 10, what about if that I was interested in that angle and I want to find cos of alpha? Well, now I can also find cos of alpha because I've worked out that h is root 10. And if we're talking about alpha, then let me just change to a green highlighter. Talking about alpha, well, this is the adjacent, because for cos I need adjacent hypotenuse. This is the hypotenuse, so that's going to be also 1 over root 10. So cos alpha and sine theta are the same, which nicely leads us to another key fact that we need in our toolkit, is we all know that sine theta is the same as cos of 90 minus theta. And 90 minus theta is, sure enough, alpha. And sure enough, we've just shown that cos alpha is equal to sine alpha. And the opposite's true as well. Cos of alpha should also be equal to sine of 90 minus whatever angle you're talking about. And sure enough, we just shown, well, sine of 90 minus alpha is sine theta. And yes, we've shown those two are the same thing. So nicely covered those two non-calc methods, key methods. They're a strategy. Next thing, trig equations have an infinite number of solutions, and that's what makes them confusing, because it's not just 1, 2, 3, 5, it's infinite, forever. So here is a sine curve with a number of periods. And if I just go back to our normal sine curve with just one x, we've got two solutions here. And if I just double click on that and maybe set up another slider, let's just do that quickly. So I'm going to make it, well, I'm going to call it C actually in this case. And yes, okay, let's make it go from -1 to 1 actually for these purposes. Just go up by 0.1, and you'll see why in a second, so don't worry if you're not following. And so now that when I move this, I want that to connect to my blue line. So I'm going to double click on the blue line and say don't equal a half anymore, equals whatever my slider C is worth. Great. So, okay. So, and what I'm saying is in one period, so remember a period is from one maximum to the next maximum, or from one minimum to the next minimum. A bit more complicated with x-intercepts because it's not from one intercept to the next x-intercept. That's only half a period. So you need to go from one x-intercept to two intercepts later. And so the period here is 360, i.e. it completes one full wave, a maximum with a minimum, and 3 x-intercepts every 360 degrees. That's what a period is. How long does it take to complete a full single wave? And the number of solutions within one period, at most in any trig equation, is going to be 3 when it goes through all the x-intercepts, 1, 2, 3. And outside of that can only be 2. And pause the video and answer this question. When can it be 1? At what points on this sine x curve up to 360, starting from 0 degrees, could there be only one solution? Welcome back. Yes, indeed, it's when it's at the maximum or the minimum. So that's -1 or 1. So when sine x equals 1 or -1, that means it's at a maximum or minimum. There's only one solution. Otherwise, there's 2, unless it's going through the x-intercepts, in which case there's 3. So when you solve trig equations, you should expecting 1, 2, or 3 solutions in one period. And that's true, look at this, even if it's sine 2x. So sure, okay, that's 1.5x, a bit more tricky, we'll avoid that one for now. This is sine 2x, so there's that 2 tells us how many waves in 360. So instead of one wave, we've now got 2 waves. There's 360. Let's just increase the size of the font so you can just see those numbers a bit better. Is that going to make it too big? A bit too big. Let's just make it a little bit smaller. Perfect. Okay, let's go with that. So look, it goes maximum to maximum, and I don't quite get the third maximum in, but if I go right from the start, 0, there's 2 intercepts, that's 1 period, and then another 2 intercepts, that's 2 periods. So there's 2 waves, sorry, not, there are 2 periods, there's 2 waves in the standard, the initial 360 degrees. And that's why this is a sine 2x. That 2 tells us how many waves. And so how long does it complete one full wave, which is what the definition of a period is? What's the domain of x within which it completes one full wave? And that could be time if you're doing it in the context of tides and things like that. It could be many other variables also. It could be chemical amount of a chemical during a reaction. Then it's always 360 divided by this number b, so 180 degrees. So when it's 2x, it takes 360 divided by 2 to complete one full wave. When it's 3x, it takes 360 divided by 3, which gives us 120. 120, it's gone up, it's gone down, it's come back to where it started from, and sure enough, there's 3 x-intercepts. So I know I've completed one full wave, and that only took 120. And that 3 also tells me if you looked at 360, you should get 3 waves. And indeed we do. 1 wave, 2 wave, 3 waves. But you'll notice, look, in one period, I've still only got the 3 solutions because 120 is now the period, and so there's still only 3 solutions. So whether that's 3x or 4x, 4x, a period, one full wave is now 90 degrees, but there's still only 3 solutions in one period. Or 1x, there's still 3 solutions. But the number of solutions within 360 degrees will double if it's 2x. So I can see instead of 3, I've now got 6 solutions. If it were, let's change that C value so we only get 2 solutions. Let's make it to a half. Let's get that as a half. So normally it'd have 2 solutions in 360, but now because it's 2x, it's going to have 4 solutions in 360. So you see the horizontal line cuts the sine 2x graph 4 times. And if that was sine 3x, it would have 3 times as many, so 3 times 2, which is 6 solutions in 360. That was 4. It would have 4 times 2, which is 8 solutions in 360. And sure enough, it does have, here's 360 degrees, 1, 2, 3, 4, 5, 6, 7, 8. So actually, this number in front of the x tells you how many more times solutions it will have compared to a normal sine x curve. That's helpful too. Once you've got those solutions within one period, okay, so I'm just going to go back to a normal sine x curve now. Okay, and if I was solving when is sine x equal to a half, well, it's equal to a half at 30 degrees and at 150 degrees, which is what you expect, 180 minus 30. Then I also have to add on periods, because look, if I drag this x-axis, oh yeah, that's going to happen every period. So this 30 degrees plus 360 is the next one at 390, plus 360 is the next one at 390 plus 360, indeed, well done, 750, and so on and so forth. So once you've found the solutions, you then have to add lots of the period on. And that's also applies to the negative part as well, because it goes infinitely onwards in the negative direction. So what are we emphasizing here? Remember, the key thing about trig functions is they have an infinite number of solutions. Let's just go back quickly. They can have, at most, in one period, we've got our sine x curve. I just drag that to one period, which is 360 degrees. There it is, 360 degrees. At most, it can have 3 solutions, and that's when we're trying to find, that's when we're looking at sine x equals 0, because it will be the x-intercepts. Normally, it has 2 solutions, and exceptionally, it will have one solution when you answer, when it's at the maximum or when it's at the minimum. Okay, so 1, 2, or 3 solutions, and then add lots of the period to get all the others. And then as you increase the number of waves in 360, 2 waves in 360, 3 waves in 360, 4 waves in 360, you can times the number of solutions by the number of waves. When you solve trig equations, I'm looking at this area. Let me get the highlights so you can see where my cursor is. I'm here. When you solve trig equations, just like you solve normal equations, you do BIDMAS in reverse, SAMDIB, SAMDEP if you're American, because PEMDAS, sorry, that should have been SADMEP. Okay, we'll look at that in a second. You've got to remember, really important, most common mistake is when are they negative and when are they positive? And we're going to do a question on that very shortly. Cos, sine, and tan in this bottom quarter, i.e. between 270 degrees and 360 degrees, or 3 pi over 2 and 2 pi, because we work in radians at standard level unless the question says otherwise. Only cosine is positive, tan and sine are negative. What do I mean by that? You tell me, freeze the video. Okay, ready for the answer? That means that sine of 280 degrees will be negative. It will be less than 0. And tan of 280 degrees will be less than 0, whereas cos of 280 degrees will be a positive ratio. Let's use a non-calc ratio to put that in context. So if I wanted sine of 315 degrees, it's going to be negative 1 over root 2, because cos is negative. If I wanted tan of 315 degrees, which would be the same as tan of 45 degrees, remember, that's the triangle we set up. Tan of 45 degrees is 1, because it's an isosceles triangle, but it's going to be negative because we're in this area here. It's 315 degrees, it's not 45 degrees. However, cos will be positive 350 degrees. It will be positive 1 over root 2. They're all positive here, sine, cos, and tan. Only sine is positive between 90 and 360, 180, sorry. And only the tangent is positive between 180 degrees and 270 degrees. Okay, and convert that into radians. And then quadratic trig equations. Well, yeah, you've got an equation like this. We're going to rearrange this and then solve it as we would a normal quadratic. And then the last one is use your trig identities. You might have to prove a trig equation. So there's nothing to solve. They just want you to prove that this is true, or that you might have to solve it but using a trig identity. They are the key methods. That one-page summary is the methods you need to know. They're the tools you need in your toolkit with which you can think and problem solve each problem that comes up on the exam. And I've chosen trig equations because it's a common difficulty. Right, let's then start with how we solve equations just by using the same method that we solve all equations with, bid mass in reverse, SAMDIB, or SAD-MEP if you're American, because it's PEMDAS, parentheses. So here's one I made earlier, for those of you that know Blue Peter. For those of you who don't, it's debatable how much you're missing. So are there any subtractions or additions? Because if there are, and I'm solving an equation, I have to undo those first. Well, yes, there is. There's a -1. So that's what I'm going to do first. I'm going to get rid of the +1. I'm going to take 1 from both sides. So nothing new at the moment. We're just solving equations the same way we always have. Are there any subtractions or additions left to do? No, they're not. We've transferred it over to this side, so there aren't any. So then I ask myself, okay, well, are there any multiplications or divisions to do? Yes, there is. There's a times by 2 here, so I want to divide both sides by 2. Great. So now I know cos 2x is -1/2. Now you just solve it as if it weren't cos 2x, okay? Because we're still doing SAMDIB, and you can't get into this indice. You can't get at this bracket. Sorry, I didn't mean to circle the indices. You can't get at this bracket. You can't get at the fact that it's 2x and not sine x until you've solved all the possible solutions, treating it as though it were sine x, because you can't do the bracket until the end. That's the most common mistake students make. Don't touch the bracket. Treat it as if it was sine x, even if it's sine 3x, even if it's sine 4x. In this case, we're treating it as if it's cos x, even though it's cos 2x. We're going to treat it like it's cos x, and then we'll deal with the 2x, which is in the bracket, only at the end. Just like in solving equations, you can only deal with that at the end. Okay, so now we're going to solve it as though it were cos x, and that's the most common mistake students make, is don't worry about the 2x. We'll deal with that at the end. So if this were a normal cos x curve, and this was -1/2, well, -1/2 ratio is great. It's going to be a non-calc question, so it's my non-calc trig ratios. You only need to remember 2 facts. I tend to remember sine 30 as a half, and cos, why not, or sine 45 is 1/√2. And with those facts, you can say, okay, if that's 30 degrees in a right-angled triangle, sine is opposite over hypotenuse, 1/2. I can use Pythagoras to work out this one. If I do, I'm going to find its √3, because 2 squared is 4, take away 1 squared is 3, and then I square root that using Pythagoras. 2 squared equals 1 squared plus whatever this side squared is. So 3 equals x squared, so x equals √3. Quick revision of that first technique we used, and that's how I know that that side is √3. And that's why you only need to remember these 2 facts and then use Pythagoras. It's good training for problem solving to just remember the 2 facts rather than the big long table that you see many different memory ways of remembering. Use your problem solving skills. It's good practice. Great. So I know if cos x was a half, well, cos is adjacent over hypotenuse. Well, this is the adjacent when that's 30, and that's the opposite. So if I did cos of 30, I'd get √3/2. That's no good to me. I want cos of a half. Well, so I'm going to have to look at this angle instead. And so it must be cos of 60, which is the same as, yeah, well done, you've worked it out. That's the same as cos of pi/3, because pi is 180. And that's equal to a half. Okay, but we need -1/2. This isn't positive as high, it's -1/2. Most common mistake. When is cos negative? Well, you can think of it in terms of the unit circle, or you can think of it in just terms of sketching the cos graph, whichever one you prefer. Here I can see that cos is negative between 90 and 270. So now let's stop talking degrees and start talking radians. So between pi/2 and 3π/2. So I know my angle is going to be between pi/2 and 3π/2 because this ratio cos is negative. It's not positive. It's negative. If it were positive, then that could be 60 degrees, could be a solution, but it can't be in this case. Okay, so let's get rid of all of that. This is our non-calc triangle that we're working with. So cos 2x equals negative a half. That tells me that were it positive, it'd be 60, but it's not positive, and therefore it must be cos of an equivalent to pi over 3, but not in the positive section, in the negative section over here, or down here, because cos is negative here, and cos is negative here. And it's not negative in these two quadrants. You can see that in the graph. 0 to 90, it's not negative, because it's above the y-axis, so cos x, which is equal to the y-coordinates, that's what y equals cos x means, is not negative. So it's here and here that it's positive, and here and here that's negative. And because of the unit circle symmetry properties, I know that pi over 3 is exactly the same as, sorry, I've drawn that particularly badly, is the same as cos of pi minus pi over 3, which is 2 pi over 3. So if that's pi over 3 and that's pi over 3, so I've got that symmetry, then what I'm talking about is pi minus pi over 3, which is 2 pi over 3, and pi plus pi over 3, which is 4 pi over 3. And that is this angle, 2 pi over 3. And let's change color so you can make tracking that a bit easier to green. This angle all the way around to there, which is 4 pi over 3. So if you want to find what angle has a cos ratio equal to minus a half, your answer to that is it's either 4 pi over 3, I'll keep with the green being as I've got green at the moment, or it is cos of 2 pi over 3 is also equal to minus a half. So they're my solutions. So treating this as though it were just not 2x but cos of x, I would have the solutions 2 pi over 3 or 4 pi over 3. So I now know that 2x, treating it as though it was just a single x, is 2 pi over 3 or 4 pi over 3. Now that we've got rid of the cos, which is equal in the SAM-DIB solving equations to indices, so indices, which is powers, and sine, cos, trig, log also comes in at this level, cos, tan, ln of x, e of x, that's all at that level too. I've now undone that, and so now I can deal with the bracket, but it's not cos x, it's cos 2 of x. And so actually the period will be half the period of the normal cos x curve. So cos 2x period is half the period of a cos x curve. And that means I should expect twice as many solutions in the same domain. So how can I get those twice as many solutions? Well, I can do that by saying, okay, well, if it's cos 2x, instead of completing one full cycle, that's a sine curve, instead of completing one full cycle in 2 pi, it's now going to complete 2 full cycles. So by that time, it'll have gone down and back up again, and it'll do that a second time by the end. And that curve there, let's go over it in blue, is cos 2x. There's pi. That's the first wave completed. That's the second wave completed. So I divide through by 2. I'm still solving equations. 2x, so what's 1x? Divide by 2. And I've got to divide that solution by 2 and that solution by 2. And that gives me 2 pi over 6 or 4 pi over 6. And if I simplify both of those, I get pi over 3 because 2 6 is the same as a third, or 2 pi over 3 because 2/3 is the same as 4/6. So I've got those two solutions, and then I mustn't forget plus or minus. Those two solutions, minus a half's down here, is these two intersections there, but they're going to be repeated every period. I'm going to get this one again one period later. So I'm going to have to add on to that the period of 2x. Well, the period of 2x, as we all know, is 2 pi divided by b equals the period for the curve cos of bx or cos of sine x. So b in this case is 2, so 2 pi divided by 2 equals pi, which is the period. So I'm going to get that same solution pi later. I'm going to get this same solution pi later. So as well as pi over 3 plus pi, I'm also going to get 4 pi over 3, plus pi, I'm also going to get 5 pi over 3. So now I've got 4 solutions, which is what you'd expect because it's 2x, so it should be twice as many solutions. And that's exhausted them all because another period later, and I've gone beyond the domain. Look up there, yeah, we're looking up here now. It's 2 pi max, so if I added another 3 pi over 3, that makes 7 pi over 3, and that is over 2 pi, and another 3 pi over 3, that's 8 pi over 3, and that is over 2 pi. It's outside of the domain, so we're not interested in those. It's not that they don't exist, they are solutions, but we're just not interested in them. So far we've got 4 solutions. Let's box them. We've got this solution, which we simplified. So I'm going to use the simplified versions, simplified, and then added a period and added a period. But then we also need to track back, look back up the domain. We're looking at the top of the page again. Let me get the highlighter out. We're looking here. Oh, look, it also goes to minus pi. So we're also going to have to subtract lots of the period as well. So I'm going to subtract pi from here, which gives me minus 2 pi over 3. And I'm going to subtract pi from here, which gives me minus pi over 3. And I could subtract another period, so I could also go, okay, is there a 7th and 8th solution here? Is there a 7th and 8th solution? If I took away another, let's just change that. If I took away another pi and change back to blue, take pi from that solution, well, if you did, you'd get minus 5 pi over 3, and that is outside. We're back at the top of the page here, the green highlighted minus pi, that's outside of the domain. And if I took away pi from here, that would give me minus 4 pi over 3, which is again less than minus pi, so it's outside of the domain. Reminder, we're looking at the top here where that I've just rubbed all of that out, minus pi. Okay, so that's it, the 6 solutions, because the others are outside of the domain. It may seem complicated, but all you're doing is SAMDIB. You're using your non-calculator ratios, and then you're adding or subtracting lots of the period. Make a summary revision card for yourself. Don't get this question wrong. Okay, which ones have we got left to do then? Let's have a look. Let's shift back up to the top. We talked about that infinite number of sequences. We've had a look at that twice now, really, because it came back in this question. And then, yeah, I'm going to show you a lovely exam question that really brings out the key point here. We just looked at that just now because we had the example of that when is it negative and when if it's positive. Well, to solve the question we just solved, we said, well, hang on a second, this is negative a half. You see where my rubber is on the screen there? It's running around here. Negative a half, and therefore we didn't want to take the 60-degree option or the pi over 3 option because we wanted negative a half, so that was the 4 pi over 3 option or the 5 pi over 3 option. Sorry, 2 pi over 3 option or the 4 pi over 3 option. So we've looked at that too, which was this idea, and we'll look at a nice exam question related to that in a second. And the last 2 that we haven't looked at are quadratics and proving. So we're going to do those now. Quadratic. So again, I'm just solving equations. And what's going to make all of this a lot easier straight from the off is if you say, oh, hang on, as soon as I've got a cos x squared term, and there's no others, there's no sine squared, because if there was a cos squared x and a sine squared x somewhere in this equation, I might start thinking I might need this Pythagorean identity, which is in your formula booklet and would allow me to substitute for 1. You might think that. Or if there was a cos 2x, you might think about your double angle identities, which we're going to talk about in a second, which again is in your formula booklet. One of those, for example, is that's 2 cos squared x minus 1, and this one is 2 sine x cos x, same thing. But it's not, it's all cos x's. So as soon as we see that and a squared term, what we can say to ourselves is, okay, I think this is going to be made a lot easier if I say, let's call cos x a letter, any letter we like. So I'm going to call it t. And if I do that, well, cos squared x, and this is something never to forget, means cos x times itself. Okay, and if I'm causing cos xt, that means t times t, which is the same as t squared. So this cos squared x I can replace with t squared. So actually what you're solving here, cos x is t, cos squared x is t squared minus 2t. And now you've just got a quadratic equation to solve. And that's the key to these questions. Not a quadratic question, although it is, it's a quadratic equation. So then I'd rearrange. So again, we're back to our old friend SAMDIB, BIDMAS in reverse when we're undoing equations. Are there any subtractions or additions to do? Well, yeah, there is. There's this minus 3t squared, so I'm going to add 3t squared to both sides, and I'm going to add 2t at the same time, and that will get rid of those subtractions for me. So I'm going to add 3t squared and add 2t, and I can treat this just like hundreds, tens, and units. The t squareds will add up together and the t's will add up together, so that gives me 6t squared. T plus 2t is 3t, and that equals 3 because these have cancelled out. And then I want that 3 because the only way I can solve a quadratic equation is by setting it equal to 0. So I'm going to take 3 from both sides. And so now I've got to 6t squared plus 3t minus 3 equals 0, which is great because I know I can now solve this. And there's only 2 methods for solving quadratics. Well, there are more, but they come to the same thing. You can solve all of them using these 2 methods. Is quadratic formula. Will they factorize? I can give it a go. I think they hopefully will. So I'm just going to try, if I make that 3t and that 2t, and I can mess around, or I can just say, well, look, hang on, that's 2 times 3, that's 1 times 3, and that's 1 times 3. So I can take a common factor of 3 outside the brackets. 3 times 2 is 6t squared. 3 times 1 is 3t, and 3 times minus 1 is minus 3. Great, and now this is easier to factorize. Okay, so what are the factors of minus 1? Well, I've just got absolutely no choice about that. This one's got to be plus 1, and the other one's got to be minus 1. And I need a 2t and a t. Well, I want a positive t by the end of it, so I'm going to make the plus 1 times the positive 2t, so that I end up with positive t in total. And then from this, I'm still just solving quadratics. It's exactly the same method. T must be equal to minus 1 to make that 0. The only way the left-hand side can equal 0 is either if, let me get the highlighter, it's either if this bracket equals 0, or, let's undo that, or this bracket equals 0. That's a whole concept of, Nobel Prize winning concept when it was first invented, of how you solve quadratic equations. So to make that bracket 0, t needs to be minus 1. To make this bracket 0, t needs to be a half. And then I have to remember, t, do you remember that right back at the start here? Let's go up the top here. Let's box that in red. Actually, right back at the start, t was cos x. So I'm now going to substitute that back in and say, I don't really mean t. That t was just a stand-in for cos x. So what I'm actually saying is that, oh, my tracking's gone out. Bear with me 1 second. Great. So cos x equals a half, or cos x equals minus 1. And then you can use your non-calc ratios and your periods and everything else to solve it, just like we solved this one, okay, as of about here. I'm not going to go into all that detail. So the key difference here is you need to use your quadratic equations methods. Last one, trig identities. Okay, in your formula booklet, you've got these, so you don't have to memorize them. You just look them up, and we know that cos 2 alpha is actually, I've got a choice of 2 here. It could be 2 cos squared alpha minus 1, or 1 minus 2 sine squared alpha. And then sine 2 alpha there's only one option, 2 sine alpha cos alpha. And then I might also want to use the fact that there's others in there, but I'm just going to stick to these 2. Cos squared alpha plus, I think there's one other in there, sine squared alpha equals 1. And I need to prove that either this left-hand side, when I use some of these and substitute it in, gets to 1, or I need to start from 1 and show that I get to this. Okay, which would perhaps also be possible as well, because you could maybe start playing around with cos squared alpha plus sine squared alpha and try and do something with that. So replace 1 with cos squared alpha plus sine squared alpha, because using the Pythagorean identity here, we know that's true, and try and rearrange that to get the left-hand side. To me, it looks like there's a lot more stuff. That's better terminology. There's far more terms on the left-hand side that I can manipulate. So I'm going to use the sine 2 alpha, and I'm going to say, okay, so if I've got sine 2 alpha here, that's the same as 2 sine alpha cos alpha. and that corresponds to the sine 2 alpha in the original expression. And then I'm also going to remember that actually tan alpha is the same as sine alpha over cos alpha. Yeah, great. So I can times those two together. And the beauty is you might see straight away that when you do that, the causes are going to cancel. We'll come back to that in a second. And then if they do cancel, it looks like we're going to be working in sines here. So what might I use over this side? Well, look, this Pythagorean identity, it's equal to 1. So an intuition might tell me maybe I want some sine squared alphas and some cos squared alphas. So for this cos 2 alpha, I think the one that's going to maybe help me out the most is this identity, using that, substituting in that expression for the cos 2 theta term, alpha, sorry. So I'm going to substitute that in, use that one, bring it down here and say, okay, well, that's the same as 2 cos squared alpha minus 1. I'm leaving away alone this 1 on the other side. I'm just working with the left-hand side of the equation. Okay, abbreviation LHS, left-hand side. So what have I got? I've got then 2 sine alpha. Remember, you can freeze this video anytime and try and work the rest of it out yourself, and then press play to see if you're right. Cos alpha, and great, I can cancel, as we mentioned briefly, the coses, because that's divided by cos, that's times by cos, divided by cos, cancel each other out. Multiplication and division of the same thing obviously cancel out. And then on here, I've still got plus 2 cos squared alpha minus 1. So 2 sine alpha times sine alpha is 2 sine squared alpha, and 2 cos squared alpha and minus 1. Well, hey ho, this looks like a lot like what's happening with the Pythagorean identity. If I just factor out the common factor of 2, I get left in the middle with sine squared alpha plus cos squared alpha minus 1. And the Pythagorean identity tells me that cos squared alpha plus sine squared alpha is 1. So actually all of that just simplifies to 1, and I need to times that by 2. And 2 times 1 is 2, take away 1 is actually 1. And so I've just shown that this whole expression, let's get that box so you know what expression I'm talking about, so there's no doubt at the end here, this whole expression on the left-hand side, I've just shown that is equal to 1, and hence I've proved it's true. Okay, so play. Over to you. We've just covered everything really that you might want to know. I posted some exam questions that I think look at these quite nicely. I'll post this mark scheme now too, so you can check once you've had a go at them using those techniques. And here's that first question. So if sine 100 degrees equals m, find an expression for cos 100 degrees in terms of m. And so what I suggest you do to save yourself time and to practice lots of different techniques is don't actually solve the question. Just say, okay, which of those one page of strategies do I need to use? And if you were going to get it the most efficient method, you'd say it's going to be number 1 up here. Because I could say, I know that, let's go back to that question. If sine 100 equals m, let me get myself a new page here. If sine 100, I'm going to do this quick, equals m, then I can set up a right angled triangle, and I know that the sine ratio is the opposite over the hypotenuse. So if I call this an angle, theta, whatever, I know that the opposite over the hypotenuse must equal m. Well, the only way it can do that if that's the same as m over 1. And if that's the same as m over 1, then 1 must be the hypotenuse. So 1's a hypotenuse. And m, let's get a green highlighter, m must be the opposite. So I'm going to put the opposite. Well, which is opposite? That side is opposite the angle we're looking at. So that must be m. And then I can use Pythagoras. I can say, well, the hypotenuse squared, take away the short side squared, should equal this adjacent. This side is adjacent to the angle theta. And so that should equal the adjacent side squared. And so the adjacent must equal 1 minus m squared. And then I can use that. Great, so fantastic. What I've said there is that this side's m, that side's 1. The question told me that because it said sine 100 equals m, and therefore I've used Pythagoras to work out that this side must be 1 minus m squared. When you square root that, it's not the same as 1 minus m. It's not the same. Just do it. If m was 2, 1 minus 2 squared, that's 3. Square root of 3, that's what it means. Is that the same as 1 minus 2, which is minus 1? No, minus 1 and root 3 are not the same. If you're in any doubt about what you can and can't simplify using algebra, just substitute in the number and check. Okay, and then I could use that to say, okay, well, great, then I now know that theta we're talking about is actually 100 degrees up there, and therefore adjacent over hypotenuse is 1 minus m squared square root over 1, which is 1 minus m squared, and resist the urge to call that 1 minus m because it isn't. We just showed it. Over to you. Best of luck. I really hope that helps and that all your exams are going well. Very best.